Hi there. In today's lesson we're going to look at fractional exponents. So far we've looked at examples like this, x to the power of a, where a would be a whole number. And today we're going to move past that, where a could be a fraction. So to begin with, I have this here. I'm saying 3 to the power a times 3 to the power b equals 3 to the power n. So what pairs of values for a and b such that a and b plus, or a plus b equals 1? So you could have a equals 0.4, b equals 0.6. You could have a equals 0.2, b equals 0.8. There's any number of combination of a and b that can, when they're added, equal to 1. But there is actually only one combination that if a and b are equal, that when they add to, it's equal to 1. So that's if a is 1/2 and b is 1/2. So what that leads to is this idea that if you substitute 1/2 in for a and b, we get the same kind of idea, right? Like, sorry, where's my eraser? If I have 3 to the a, but if a is 1/2, that's 3 to 1/2. And if I multiply that 3 to the b, I get 3 to the 1/2. And that could be equal to 3 to the 1, because 1/2 plus 1/2 is equal to 1. Just using the same property here. And we also know that the square root of 3 times the square root of 3 is equal to 3, which is 3 to 1. So I ask the question, can you write 3 to 1/2 as a radical? And the answer is yes. In order for both these statements to be true, it's necessary that 3 to the power of 1/2 is equal to the square root of 3. So that's the kind of first example. Second example, I have something here where I have 2 to the power of a times 2 to the power of b times 2 to the power of c is equal to 2 to the power of 1. So in this case, a, b, and c, if they're all equal and they add all up to 1, that means they must be equal to 1/3. So you could have a similar kind of situation as before. If you have 2 to the 3rd times 2 to the 3rd times 2 to the 3rd, that's equal to 2 to the power of 1/3 plus 1/3 plus 1/3, which is 2 to the power of 1. And then if we also say, well, we have something like this, if that is all equal to 2, that means n must be equal to 3. Oops. So again, I'm trying to draw out this idea that, that must be equal to the same as this. So is there any kind of rule that we can see here? And it's kind of like the idea of that if that's our index is n, then the exponent is equal to 1 over n. So for example, if we come back to the to this one here, we have n is equal to 2, and the power that it's equal to is 1/2. Here we have n is equal to 3, and the power that's equal to is 1/3. So then I say, well, if you did manage to come up with a rule, you can confirm it with the rule that's written in the textbook on page 223. And I think it's basically what I just wrote here. If you have x to the power of, if you have some n root of x, that's equal to x to the power of 1 over n. So with that kind of information, I'd like you to try to evaluate this power. We can use some of the power laws that we've used before. So in other words, we can say that this is equal to 16 raised to the power 1/2 and divided by 25 raised to the power 1/2. And that's equal to square root of 16 divided by the square root of 25, which is equal to 4/5. Alright, next page. Powers with rational exponents. So here's a better or more comprehensive definition of what we sort of went through in that other side. Here's an important kind of thing to recognize is how you apply exponents and indexes to the base or radicans. It's kind of like the idea of the order of operations doesn't matter. If you start with this, you can do the fractional exponent first and then apply the power, or you can apply the power first and then do the fractional exponent as the radical. It's best seen with some examples. Here's an example. I think I took this one out of the textbook. Negative 32 to the power of 0.4. Well, 0.4 is equal to 4 over 10, which is equal to 2/5, which is what we get here. So if a person recognizes this property here, that 32, it can be factored as 2 times 2 times 2 times 2 times 2, then if we recognize that, then we know that the 5th root of 32 is equal to 2. And we use that property to analyze this first. So the first step we do is take the negative 32 raised to the power of 1/5. So the 5th root of 32 is 2, so that's where we get the negative 2. In this case it's a negative 32, so here we have a negative 2. And then we can square that, so negative 2 squared is 4. There are some more examples on page in the textbook. Perhaps I'll do another one for you though. I could do another example. I'll just try to guess at something. Say 54 raised to the power of 2/3. And maybe we're going to be asked, write it in radical. Write this as a radical. So we could do that by going 54 squared. Oops, sorry. 54 squared raised to the power of 1/3, which is equal to the cube root of 54 squared. We could also say that this is equal to 54 to the power of 1/3 squared, which is equal to let's try another one. Let's try 81 raised to the power of 3/4. So there's two different ways we could do this. We could say, first of all, we're going to take 81, we're going to cube it, and then we'll take the cube root, or take the 4th root of that, which would also be the same as going 81 cubed times 4th root. I think that's kind of hard. I think a better way to do that would be to try this first. 81 to the 1/4 raised to the 3rd. So this is equal to the 4th root of 81 all cubed. And if we went to actually factor 81, that's 9 times 9, which is 3 times 3. So there we see there's 4 factors of 3 in here. So this is the same as saying the 4th root of 3 times 3 times 3 times 3 all cubed. And we know from simplification that if we have identical factors, the same number of identical factors as there is as the index, so if the index is 4 and we have 4 of those, that's equal to that cubed. So that's 27. So I think you could see that by simplifying the 4th root of 81 first, we get a nice small number, which is 3, and then we can cube it to get 27. I think that's easier to work with. I mean, this would work fine too if you're using your calculator or something like that. It wouldn't be so bad. So that's some ideas or thoughts on why or how radicals with fractional exponents work and how we can manipulate them a little bit.